Okay, so I'm going to pick back up from our last video. Again, we're looking at one last look at superposition. We're not really talking so much about superposition as we are just multi-loop circuits and multi-source circuits, and how they're handled when they just get to be too complicated for hand calculation. So we went through this particular two-loop, two-source circuit here. And it happened to be one that we could solve by a Thevenin by arranging it properly, and we did that in the last video. We came up with 3.28 volts for our Thevenin equivalent, and then up here we applied that. We'd already calculated the R Thevenin, and we put the load in, applied the voltage divider rule, and we came up with a voltage of 2.25 volts. What I wanted to show in this whole harangue here is this idea that circuits with multiple loops, sorry about the table, multiple loops in them. This circuit has a current loop that flows like this, another current loop that flows like that, and another current loop that flows like this. Or I guess you can define these backwards if you want. It just doesn't matter. You'll get negative numbers at the appropriate places if you do that. But so this circuit has three loops in it, and around these loops we can apply Kirchhoff's voltage law. If we wanted to, we could look at this circuit. It has 1, 2, 3, 4 nodes, and we could apply Kirchhoff's current law at any of these nodes. So I'm going to stick with Kirchhoff's voltage law in this case, and we're going to look at the currents I1 and I2. If we are to write some equations for this, we would say Kirchhoff's voltage law for I1, it sees a voltage rise here because the arrow goes into negative and comes out of plus, and we see a voltage drop across R1. You can put that in if you like, and we see a voltage drop across R2 so the voltage drop across R1 is all due to this current I1, but the voltage drop across RL is due to both I1 and I2. And so we write the equation as this. We say the voltage drop across R1, VR1, is I1 times R1, and the voltage drop across VRL is I1 plus I2 times RL. And there's two ways to do this. You could say the voltage rise is negative, and you could say negative 5 volts equals 0, because Kirchhoff's voltage law in its classical form wants things to be equal to 0. But what I did is I just said that the voltage drops are going to equal the voltage rises, and we wound up with the same idea here. I got 5 volts on this side instead of negative 5 volts on that side. Likewise, KVL, Kirchhoff's voltage law for I2, I'm going to have the voltage rise here is 2.5 volts, and this really should be labeled V2. So the voltage rise here is 2.5 volts, and then I'm going to have a voltage drop across R2 that's due solely to I2. Then I'm going to have a voltage drop across RL, just like I did before, that's equal to the sum of the currents I1 and I2 passing through RL. And so I get an equation down here where I can write this thing as I2 times R2, that's that voltage drop, VR2, plus I2 plus I1 times RL, that's the voltage drop across RL, VRL, and that's going to be equal to 2.5 volts. Now, what I basically have here is I have two equations with two unknowns, I1 and I2. R1 and R2 and RL, we know those, they're up in the diagram. So if I rewrite this, I can say, well, let's see, all the terms of I1 here, I1 passes through R1 and RL, so I have I1 times R1 plus RL, and only R2, I'm sorry, the I2 portion of this is just the part that flows through RL, and so I can take this equation here and gather up the terms related to I1, and then there's only one term related to I2, and again it's still equal to 5 volts. Sorry about the shake, my bad. And when I do that, I get this equation right here. Likewise, when I look at this equation, I2 is flowing through R2, and both I1 and I2 are flowing through RL. So I separated out the I1 times RL, and then I2 is flowing through R2, but it's also flowing through RL. So I gathered that together. This is just for, mathematical convenience, and my voltage rise still 2.5 volts. And I plug in the values here, the ubiquitous plug and chug, where we put in our numbers and we get I1 times 3.7K, because 2.2 plus 1.5 is 3.7, and I2 times 1.5K equals 5 volts. In the second equation, I got my I1 times 1.5K and I2 times the sum of 1K and 1.5K. That's R2 plus RL, and I get 2.5K. And so now I have a system of equations that's pretty normalized here. Oh, I shouldn't say normalized. It's pretty it's easy to write. I can see where the I1s and the I2s are, and that's great. So if we go to the top of this page, there's the equations we just wrote. I'll just copy them over exactly. So I1 times 3.7K, so and so forth. Let's eliminate what we usually do when we have two equations and two unknowns. We want to eliminate one of the variables. So what I'm going to do is I'm going to multiply this top by 1.5. So I'm going to wind up with, I1 times 3.7K times 1.5 in this first term here. It's going to give me I1 times 5.55K. And in the bottom, I'm going to multiply the entire equation by 3.7. And as you can, because multiplication is commutative, you can see I'm going to get the same thing down here. All right. So I multiply this entire equation up here by 1.5. And I get I1 times 5.55K plus I2. Now 1.5 times 1.5, it's, if you know your squares, 15 times 15 is 225. So 1.5 times 1.5 is 2.25. And 1.5 times 5, it turns out 2.5 is half of 5. So 5 plus 2.5, this becomes 7.5 volts. And you can verify that on a calculator. But all we're doing is multiplying this entire equation by 1.5, both sides of it, so it's still an equation, it still equals, and we haven't hurt anything. The bottom one we did by 3.7, and that gave us, down here we got I1 times 5.55K plus I2 times 3.7 times 2.5 comes out to be 9.25, and there's a K in there, so that's K, and we get to cheat on this. 3.7 times 2.5 is 9.25 volts. So now what I can do is, in essence, multiply this equation by -1 and add the equations together, or just subtract this equation from that equation. Some people would say, well, you multiply this by minus 3.7, and you get this, the whole thing, and then you add the two together. It's all, it all comes out to be the same oatmeal. So, all right. So I1 times 5.5K minus I1 times 5.5K gives me 0. I2 times 2.5K and I2 minus I2 times 9.25K, well, that's going to be minus 7K. So I get minus I2 times 7K. And up here, I've got 7.5 minus 9.25. You'll find that that's negative 1.75 volts. And now I2, I can divide both sides by minus 7K, and I2 is equal to minus 1.75 volts divided by minus 7K, and it's equal to 250 microamps, or we can also write that as 0.25 milliamps. Now this one is more correct in terms of engineering notation, but when you're working with k-ohm resistors, sometimes it's handy to use milliamps, because when you multiply milliamps times k-ohms, you get volts. All right? So let's slide this up. So we just found I2 right here. All right, and that's great. Now we can find I1 by substitution. If we look at our top formula up here, I1 times 3.7K plus I2 times 1.5K equals 5 volts. So let's go ahead and use that, and we'll substitute in what we now know is I2. I1 times 3.7K plus I2 times 1.5K is 5 volts. I get I1 times 3.7K plus, this turns out to be 0.375 volts equals 5 volts. Now if I subtract 0.375 volts from both sides, I'll get I1 times 3.7K equals 4.625 volts, and then I can divide both sides by 3.7K and get that I1 is equal to 1.25 mA. Now, we know that the voltage through the load resistor, let me put that circuit diagram back up here. The voltage across the load, did I say through? I am so sorry. We know the voltage across the load resistor is equal to the total current through that load resistor times the load resistor. Well, the total current through the load resistor is I1 plus I2, and so the voltage across the load resistor is going to be I1 plus I2 times RL. So we come down here and we say VRL equals I1 plus I2 times RL, what we just said. So I got 1.25 mA plus 1/4 mA times 1.5K gives me 1.5 mA times 1.5K. Again, 1.5 times 1.5 is 2.25. mA times K is volts. We get VRL equals 2.25 volts. And going back to our Thevenin solution, we got the same answer. So either we're profoundly lucky, or we actually did something correctly. I like to assume it's the latter. So the whole point of this exercise, and I'm going to ask you guys to do this same problem, I believe, compared to the homeworks and labs you've already done on this, that this will not be hard from a superposition standpoint, and you'll probably be, in essence, doing a lot of what we did in this Thevenin thing, because superposition has some flavors of Thevenin and Norton in it, where you look at you deaden sources one at a time and you do that sort of thing. But that will be a one problem homework. The whole point of this, though, is if you can imagine a big circuit, some amplifier or several stages of amplification or filtering, where you've got many loops like this. Some of them may not even have sources in them. Some might have current sources. In the case of a transistor, or in the days of vacuum tubes, you oftentimes modeled parts of those devices with dependent sources, where a voltage or current on at one set of terminals gave you a current through the device, that valve type action. And so you would apply these rules we've done And you could try to solve the circuit with Thevenin or Norton or superposition, but if the circuit gets too complicated, you probably have to resort to a many equation and many unknown system. And that's what circuit simulators do. That's the whole point of this harangue that I'm doing now, is that circuit simulators like SPICE, which we have used, break the circuit down into, they process your graphic schematic file, break it into loops and nodes, and they look at all the Kirchhoff voltage law loop equations, and they look at all the Kirchhoff's current law node equations, and they calculate all the currents and voltages. And what they do is, what do they do in the case of inductors and capacitors? Well, what they do is they make a calculation, and then they know that the inductors and capacitors follow certain rules as far as what they are doing to the voltage, changes in voltage or changes in current, and they apply those what they call element relations, and the process continues on, and they do this for little time slices. So they calculate it once, and then again for another little increment in time, and then again for another little increment in time. And they keep track of all those results, and then you can plot out any particular voltage or current that you want. And if you've modeled the circuit as accurately as you can, the voltage or current waveforms that you see will be a good indication of what's going on in real life. Obviously real life, there's always, extra little effects of capacitances and inductances that we may not have modeled. But, people spend a lot of time trying to capture all that information so they can analyze circuits, because it's expensive to build a printed circuit board unless it's a small prototype board to try some small circuit. It's expensive to build an entire circuit board for a product, and then have to change it if there are changes necessary. Likewise, it's even more expensive to build an integrated circuit, and SPICE especially was designed because of this cost of that building an integrated circuit is such a big job and risky, that they said if we could simulate these circuits better and better and better, then we'd have a much better chance of getting our integrated circuit designed and built in the least number of passes, because every time you change the design and put it through the whole integrated circuit design process, you spend a lot more money. So that's why simulation is so desirable in analog and digital circuits too. It's just to get correctness on board or integrated circuit designs, and to minimize risk of having to respin something. And both those processes, not only do they cost money to make a printed circuit board or an integrated circuit, but they involve lead times. And so if you put your project on a schedule, and there's a thing called the Gantt chart, which shows your project schedule, and you're meeting every week and seeing how things go. Well, if people get through a certain part of the design, then realize, oh, that's not going to work, we didn't realize that this, that, and the other thing don't work, now we have to go back and do something, the whole project has to move out in time, and that's never desirable. So again, this multi-loop, multi-source, math-intensive method is what is done in circuit simulators, and we needn't go in and study exactly what they do, but this just gives you a flavor that something a computer can do, tons and tons and tons of calculations, is why we can run our SPICE simulations on Easy EDA or LT SPICE or Circuit Maker or what have you, and wind up with results that indicate if our circuit's going to work the way we want or not. All right, so that's that's that. I'll post a homework problem with this circuit in it. If you want to get started on that using superposition, great. You'll see the paper posted here shortly. And so we'll be moving into active circuits now. Transistors, op amps. Maybe we'll have a couple review circuits on op amps, and everything we do with the ADALM 1000 and ADALP 2000 parts kit. What's going to be interesting for us is that those things only work on 0 to 5 volts. All our stuff we did in ELE 115, we're able to use, say, like plus 12, minus 12, that thing, bipolar power supplies, and that's really a handy way to go. But a lot of circuits can be built using a single power supply, and so we'll be adding some features into our circuits to make it so we can run in a single power supply, and that'll help us learn a little bit about DC and AC components and why we need to pay attention to them in circuits and that sort of thing. All right, take it easy, and we will see you next time. Bye.